time to start talking about angular momentum. We're following the theme that we've been doing for about a month or two of doing the rotational version of all the linear things that we know. We know about momentum, and that's just mass times velocity, but now we're going to talk about angular momentum. Let's relate it to what we already remember. So this is Newton's first law, written in terms of momentum, and it says objects with momentum will keep their momentum unless acted on by an outside force. And true to our theme of making the rotational version very simple and very similar to the linear version, objects with an angular momentum will keep their angular momentum unless acted on by an outside, not force, but a torque. So instead of a force, we're looking at the rotational equivalent to force, which is torque. Okay, we remember momentum P equals mass times velocity. Well, it's just like before, it's going to look just the same, so it's going to have the same equation but different letters. So angular momentum is written down as the letter capital L. I do not have an answer why it's capital L, just think angular, and the L, capital L, will help you think of angular momentum. And we already know mass and velocity as far as their rotational equivalents. One of them is the moment of inertia, I, and the other one is angular velocity, omega, or as some of you love to call it, wombo. And here I'm going to do a quick derivation of a different form of angular momentum. I don't know if you noticed this, but every moment of inertia has something in terms of mr squared. And then, so I'm going to substitute just a general mr squared in here. And this is a lot of hand-waving stuff here, so just kind of showing you where it comes from. And omega, or wombo, we can write that as v over r, because as we know, v equals r omega. And if I solve that for omega, then it's v over r. So I'm going to make that substitution in, and as you notice, it's going to cancel out one of those radiuses. So let me rewrite it again over here, and it'll be mvr. So this kind of makes sense if you think about what mv is. mv is just momentum. So angular momentum is just the linear momentum times the radius, just like the torque is a linear force times the radius. Okay, now we remember in conservation of momentum, that means the momentum total before will equal the total momentum after. Well, it's still true with angular momentum. So the initial angular momentum L equals the final angular momentum L prime. Now, this prime here does not mean a derivative. That is not any calculus term at all. This prime is just to show that it is different than the first one, and to show that it is the final momentum rather than the initial. Let's do an example. So we have a figure skater, and they are spinning in a circle, but their arms are stretched out really far, and they are spinning at some angular velocity. And so we're going to make some changes on how they are spinning to show that the angular momentum is conserved. We know that angular momentum is the moment of inertia times angular velocity, so just mass times velocity, but in the angular terms. Well, that initial I omega should equal some final I omega. So I could change either the moment of inertia, or I can change the angular velocity. So what I'm going to do is I'm going to change this. Remember, this depends on the shape and the radius and the mass and everything. So if I pull the arms in, and you could probably think about this if you've ever watched figure skating or ice skating, that when they pull their arms in closer, they spin faster, and this is why. All right, so I'm going to make this I smaller by reducing the radius. So they pull their arms in closer, so that gets smaller. And if the initial angular momentum equals the final angular momentum for it to be conserved, that means the final angular velocity needs to be larger. So if one goes down, if one gets cut in half, the other one has to double. That's the only way for it to be conserved and be the same. Now, let's do an easy example really quick. Okay, so I've got a disk, and it is rotating at some angular velocity. And that angular velocity is this. This is 80 revolutions per minute, so pretty fast. And it has a moment of inertia. I'm not going to make you calculate it. I'm going to just give it to you. It has this moment of inertia. And what I'm going to do is I'm going to try to apply the conservation of angular momentum. So if I end up dropping a spherical ball right on the center of the disk, then what I'm going to be doing is I'm going to be adding some mass. I'm going to be adding a new moment of inertia. So it should change the angular velocity, just like we talked about with the figure skater. So there's the after picture. I drop the ball on the disk, and then it's going to have a different angular velocity. So we need to know a little bit about this ball. The ball has a mass of 6 kilograms and a radius of 8 centimeters. So we need to calculate its moment of inertia. So I gave you the first one, we have to calculate the second one. And the question is, what's the new rotational speed here? What's the angular velocity of the disk after I drop the ball on it? We know that initial angular momentum equals the final, so that means the moment of inertia times the angular velocity equals the final moment of inertia times angular velocity. So we are going to be changing this by adding the mass of the ball to it, and then it's going to end up, as a result, changing the final angular velocity. Okay, so we need to make a couple conversions before we plug everything in. We have 80 revolutions per minute to start with, so I need to put that in radians per second. So we make our conversions here, cancel out revolutions, and then we multiply by 2 pi, and multiply by 1 over 60, so that we can get everything in terms of radians per second. So there it is. We have 8.38 radians per second. Now, before we do all the rest of the math here, try to think about this and make a prediction in your head. If this thing is spinning at some angular velocity and I suddenly drop weight on it, start to think now, do you think this final angular velocity will be more or less than 8.38? So think about what makes sense, what should actually happen, and then we're going to actually calculate it and show. So our initial angular, our initial moment of inertia we already had, but this is the final. So it's going to just be both of them added together, because it's going to be the moment of inertia of that cylinder plus the ball, because they are now both rotating. So we just need to add them together. So the moment of inertia of the ball is a sphere, and this is something that's given. This is the formula for a sphere to find moment of inertia. And we just need to plug and chug and calculate what that actually is. It turns out it's this. So all I did was plug into my calculator to get this as the moment of inertia of the ball. So now we can find the final moment of inertia. And that just means we have to add them together. So I'm going to add the first one plus the second one. And now that was given, and then this is what we just calculated. So I crunch the numbers and I get that. That is my final moment of inertia. So now we can actually see what it would look like as far as conservation. Now we can use our formula here. So I know what this is, I know what that is, I know what this is, and I want that. So let's calculate it. Alright, let's solve this for the final angular velocity. Now remember, our number we were looking at before was 8.38 radians per second. That didn't work. Radians per second. That was the initial. Is the final angular velocity going to be greater than, less than, or what if, I don't know, could it be the same? We don't know. Let's calculate. So we've got just to plug in everything that we know. We know the initial moment of inertia was 0.075. We know that the initial angular velocity is 8.38. That's what we're trying to figure out. It's going to be more or less. And then our final moment of inertia was the sum of the cylinder plus the ball. So what's our number? It turns out it's less. Okay? If you think about this, it makes perfect sense. If you had thought of this in a linear sense, you have a truck going down the highway, and let's say this truck is just coasting. It's not pushing on the gas or anything, and then all of a sudden you dump a ton of weight in that truck. It's going to have to slow down because there's so much more weight at it. Well, in this case, we have something that's rotating at a certain speed, and I added weight to it. I added more mass. And turns out, for the momentum to be conserved, it has to slow down because the mass increased, so the velocity had to decrease. But in this case, it's rotating, so the moment of inertia increased, so the angular velocity had to decrease. So it was less than what we had before. So this is what we had. We had our initial equals our final, and that was it. So as a recap, our final moment of inertia went up, so our final angular velocity had to go down. Makes perfect sense here. So that shows, or that is because the angular momentum is conserved. So that is the idea, that the momentum is conserved. All right. For this example, I'm going to do a part 2 video because this one is about at 12 minutes. So tune in for part 2 for a different kind of example of conservation of momentum.